Hi there! This video series is to display my problem-solving and learning abilities. I hope to show that I can solve any programming problem, regardless of whether I already have expertise in the language at hand. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. For now, I am learning Python. I have no professional experience or formal training in the language, and have only been learning it since mid-January. While I'm picking up fairly quickly, I cannot claim any real expertise. Today, I am going to show my approach to solving this 10th Project Euler problem, starting fresh, talking through my thought process. As always, I will link to both Project Euler and my repository in the description. Let's dive in. Summation of primes. The sum of the primes below 10 is blah 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 17. Find the sum of all the primes below 2 million. Let's see. So, I have a feeling that the naive approach just won't work here. Gotta open my IDE, but let's see. So, problem10.py, problem statement, and by won't work, I mean won't work within the 1 minute time limit that Project Euler gives, because I am sure it will work eventually. It's more a question of when. That. So let's do our little primes equals array. Throw the number 2 in there just to give it a prime. And then try to remember which problem was it that I last looked at primes. Looks like it was this one. I'm gonna copy sort of some of this logic. Okay, so is factor is going to be exactly the same as we've used before. Is prime, again, exactly the same as we've used before. And this is prime method might be slightly less than peak efficiency, but I also think that that's not where our slowness is going to come from. Because what I think we're going to end up needing to do is somehow make it so that we're not going through all of the numbers. But let's start with the naive approach as usual. So for n in range 3, and 2 million itself is, of course, not a prime. So I think that if we skip 2 million, it's completely fine. And actually, let's pull this into a variable to be like target max. And then we'll set that up here. Target max equals 2 million. Now I gotta recheck my number of zeros because I always lose count. Okay, 3. That is the right number. And actually, because, again, Python, we can just do the check whether it's prime, because that check appends our little, our number to our array. And I actually want to start at 3 and step up by 2, because why bother even looking at all of the even numbers? And that'll reduce us from 2 million to 1 million right off the bat. And we don't need a break, because that's what the for loop is going to do for us. Okay, so then we want to print, and just for sake of seeing what it do, I'm going to use the sum method. I can almost think of a way to make this slightly more efficient. Something to do with setting it so that it doesn't keep looking at numbers that are primes above the square root of the number being checked. I don't think I quite know how to do that in Python, so I'm going to let it ruminate just a tiny bit. And I'm actually going to go ahead and print out this, because I kind of want to know how long this part takes. I have a feeling since it's Python, it'll be like, this takes less than a second. Let's go ahead and check how this algorithm works. And again, like I said, I don't really expect this to finish in under a minute. We'll see how well it does. Let it run for at least 2 minutes here. And let me kind of talk through a bit more what I actually did, since I didn't really talk through it. Obviously, this is factor and is prime methods we've worked with in several different projects. You're supposed to have 2 spaces after the definition of a function, according to some linters. So basically all I'm doing is I'm saying for odd numbers starting at 3 until they get up to 2 million, check whether they are prime, and of course if a number does get tested to be in a prime, it gets added to this array. And then I just use this built-in Python function called sum to sum up the arrays. And it is still going through 1 million numbers. And for each of those numbers, it's going through the number of primes that exist in the array. So let's see. Let's throw a little bit check here. So if I is greater than the square root, let's go look up how to do a square root in Python, because I forget. Python square root. Right. This little exponent thing. Possible prime. Then I want to break, because if like say we're checking the number, let's say the number 25. 25 is 5 times 5. No number bigger than 5 can be a factor in 25. So by the time we get to 25, we're going to have so many different primes, right? Quite a few. Not actually certain how many. Let's see. 2, 3, 5, 7, 11, 13, 17, 19? And I think 23. Not 100% certain, but like close to 10, right? We only need to check 3. We only need to check 2, 3, and 5, and then if we're looking at 25, we're like, oh, 5 is a factor. We can just return false. So let's go ahead and stop our little function. It's been running now for about 4 minutes, which I would say obviously 4 times more than Project Euler wants. Let's see if we can get this to run any faster, like within the next 4 minutes. I still think that it most likely is going to take longer than the 1 minute limit. So while that is going, let's try to think a little bit about how could we make this more efficient. So we know we're only checking odd numbers. So here's something that we could do. We already know we're only checking odd numbers. Why have 2 in the primes array? That should eliminate 1 million checks, basically, right? Then we're going to want to have a +2 here. Not +20, because that would be a little too many. I don't want to continue running this when I know that I've made it just even slightly more efficient. So let's restart. Let's see. So we've already got it set up so that it only check primes up to the square root of the possible prime. Well, effectively up to the square root. There's like an off by 1 error in that analysis. But, yeah. 2 most common mistakes that programmers make are off by 1. Let's see, so we've got the range going from 3 to 2 million, stepping with 2. I almost feel like I almost feel like I have an idea of how to make this better, but it's not clear. Let's see, we're already going through all of the odd numbers only. Is there a more efficient way of doing this? I mean, to be real, there is, right? Of course there is, because there wouldn't be an unsolvable problem on Project Euler. Thousands of people have solved these first 100 problems. So let's see. I do feel like going from the smallest to the largest does make the most sense. So far as, let's just check to see if it has any prime factors, and if it does, then it's not prime. So, nothing comes immediately to mind. But obviously our little algorithm has been running for over 2 minutes. I do want to see if we can get it to complete running and just sort of see if we get a correct answer, even if it doesn't meet the time limit. But just for sake of trying a little harder, let's see. What's a good thing to Google to find a more efficient solution to this without finding literally the exact answer to this problem? Let's see. We could look for a more efficient way to discover whether a number is prime. So let's say Python find prime. Okay, so Python program to check prime number seems like exactly what we need. We of course have the first few prime numbers here already, which one thing that we could do to make our program just even slightly more efficient is to list out the first few primes, since, like I just demonstrated, I kind of have the first several memorized, but that ultimately won't help us all that much. So all the numbers starting from 2 to n2 using a for loop, and check each number. For every number, check if it divides n. That's less efficient than the algorithm we have right now, because they go all the way up to n divided by 2 plus 1, whereas we only go up to the square root, and also we're not checking all numbers, we're only checking primes. So not quite. Square root of n. And here it's like time complexity is square root of n, which is fair. Ours, I would say, probably has a time complexity similar to n square root of n, or n times square root of n. Oh, there's apparently a square root function that I could import from math. That could be better. And then it says maybe you can use recursion. So if the iterator is 1, return true. If num divided by the iterator equals 0, return false. So basically, if whatever number you put here can evenly divide into here, then it is not a prime number. And then at the end, we call it by itself. Although I would honestly write this a little bit differently now that I'm learning a little more. I would say just return this, because you can kind of see just by looking at it, if the return of this function is false, then we're returning false, and otherwise we're returning true. So this is written in a little bit redundant way, although I would say possibly more clear, which, you know, sometimes writing your code so that it's more clear, and by sometimes I mean basically in every single case, is a better strategy than writing it so that it's very efficient looking code. And let's see, we have the num13, iter equals an int that is the square root plus 1, so like for 13 the square root is going to be somewhere between 3 and 4, so we're going to give it an iterator of 4, I think. And then send num 13 and 4 into our recursive function. 13 and 4. So iter is going to be 4 at first. 13 cannot be evenly divided by 4, of course, so we go on to the next check. And then we call the function with 13 and 3, go through, check it. I honestly think that this is less efficient than the method that we have right now. Oh, look, this is the method that we have right now, I think. Okay, it actually is not, maybe. Loop through all numbers from 2 to the square root of n, rounded down to the nearest integer. If n is divisible by any of these numbers, return false. Okay. So again, because they're looping through literally every single number between 2 and the square root, or let's say the nearest integer to the square root, counting up, rounding up, again, just slightly more inefficient, because like for 11, it's going to test... Ooh, here's where it gets clever. So 11 is also somewhere between 3 and 4, so I think this is also 4. But it's still going to test 2 and 3. If we put 25 in here, and go here, it will test 2, 3, and 4, then 5. So our algorithm would not test 4, because we already know that 4 is not a prime number. So our algorithm is still just slightly more efficient. Obviously not as efficient as we want it to be, but slightly more efficient than the ones we're seeing here. Using a while loop to check divisibility, so this is another just... And again, they're plus equals to 1 here, when they could have another check and then start at 2, or start at 3 plus equals to 2, and have it skip half the numbers. And this is just the same thing, but we're using math. There is a method, I guess we could import a library that would check as prime for us. But again, I don't see how that's more efficient than what we have. So based on this article, it looks like for checking whether a number is prime, we actually do have the most efficient algorithm we're likely to find. Let's see whether the program is done running. And it is. Okay, so it took a total of... Okay, about 9 minutes to get the number. And you can see this sum function is actually like... Let's see, the sum function took fraction of a second. Like, I think this is a fraction of the amount of seconds and not milliseconds. In which case it took 0.4% of a second to do the summation. And just out of curiosity, I want to go ahead and check whether this number is correct. And if it is, we still have some work to do, obviously, because we didn't write an efficient enough algorithm. It took 9 times longer than our time limit. Let's see. What's this little thing? Oh. Well, that's convenient to know about. That'll save me some time later. Problem and pen. Yeah, this has been solved by 34,000 people, so I'm gonna guess that some of them are going to cheated just like I'm kind of about to. Oop. Okay. Doo-doo-doo-doo. Okay, so we got the correct answer. And I got a nice, neat little award. However, we didn't solve it correctly, I would say. So correct answer, inefficient algorithm. Let's see if they have documentation around this one. And they do. They also have quite a lot of discussion boards. Okay, let's see if we can wrap our heads around this. Okay, so if it is prime, then okay, so this one has it starting at 5 and then going by 2 and then like going by 4, which does not quite make sense to me. Okay, so we might want to look at problem 7. Okay, so it's saying we could have the limit, start with a sum of 5, have n that starts at 5, because we know 2 and 3 are prime, go through into the limit. So if it is prime 5, then sum equals sum plus n. Go to 7 if n less than or equal to limit, which 7 is, and is prime 7. Then add that, then go to 11. So I think this is slightly more efficient because it's skipping numbers divisible by 3. To find all primes up to 1 million, testing only numbers not divisible by 2 or 3. Over 20 million divisions are carried out. Finding the primes up to 5 million takes over 200 million divisions. That is an awful lot of work. How can we substantially reduce it? That's the question I came here to find. Apart from some rather advanced new methods, the best answer to that question is over 2,000 years old. When you want to find all primes below some limit, use the sieves of Greek name. Let me see if I can try this. Eratosthenes. That's probably pretty close, right? I'm gonna pretend it is. When you want to test just a handful of not too large numbers, trial division is adequate. However, suppose you'd want to test a few hundred numbers between 10 to the 9 and 10 to the 10. Then a mixed strategy is good. First, use a sieve to find the primes up to 10 to the 5th, then perform trial division by those primes. Okay. So this is, again, it's suggesting, like, use the primes. And just for the sake of curiosity, I'm going to go ahead and pull up number 7 here. Not the check mark, the little PDF. Helps to click the right thing when you're trying to look for something. Okay, and here they have some very specific, like, if n equals 1, return false. If n equals is less than 4, return true. And then here again, we've got some basic checking for the first several primes, making it like an n of 1 for the first several. And then this checks for if it divides by 3, which, again, I think that our method is a little more efficient than doing all of this, because it's basically saying we are already doing number 2. Yes, the number 7 might take a little bit more time. But in any case, so floor of the square root of n, start with the number 5, and then if n mod f equals 0, return false. Otherwise, n mod f plus 2, and this is f equals f plus 6. So let's look through it for the number 5, so we can kind of understand the math a little bit. So 5 is less than, and I'm going to pretend the number is 17 right now, just to, like, think through it. Maybe 19 is better. No, we'd probably want a larger number. Let's think about, like, let's say n is 100, or 101, actually 101, because that way it's not evenly divisible by 5 and we don't get kicked out immediately. Square root of 101 is between 10 and 11, I think. Square root of 100 is 10. So it would be just slightly more than 10. So our r would be 10 here. So obviously 5 is less than or equal to 10. 101 divided by 5 is not going to equal 0. Or is not going to have a remainder of 0. 101 mod 5 plus 2, which is 7, also going to be 0, because 101 is not evenly divisible by 7, I think. Let's see, so it would be 10 divided by 7 is 1. 31 divided by 7 is not a clean number. Is not a whole number, for sure. So then we're at f is 7. Or no, f is not at 7 here, is it? Because we don't reset f, we just add 2 to it. So when we set f equal to f plus 6, we're not setting it to 7. We're setting it to 11. And then 11 is not going to go back in here, but let's ignore what I said n was for a second, just for thinking through this. So 11 less than or equal to r. In mod 11 is not accurate, then is not 0, then we continue. In mod 13 is not 0, then we continue. And this is so we say 11 plus 6, so 17. Okay, so this is showing us the pattern in primes. Interesting. So I kind of think that this is not going to be any more efficient of an is prime method than the one that we currently have. In fact, it's basically identical. identical because it's manually saying these are all of the primes. Whereas we're just being like, oh, this number is a prime, throw it in the thing. The only thing that is not there is this in mod 3 equals 0. But again, like, we have that, right? Because we're checking 3 and we're not looking at anything but odd numbers. So we're checking 3 first, just like this algorithm does. Okay, so we start with 1, which I kind of disagree with this one again. Start with 3. Then if it's prime, then count equals count plus 1 till count equals limit. Okay. So again, I think we have the most efficient method. That is trivial, at least. Let's see if we can understand the sieve of Eratosthenes or something. I still feel like it's probably more likely to be Eratosthenes. Probably not Thenis, but Thenis. I am not a Greek student. The basic idea behind this ancient method is that instead of looking for divisors d of n, we mark multiples of d as composites. And every composite has a prime divisor. The marking of multiples need only be done for primes. The classical algorithm is make a list of all numbers from 2 to n, find the next number p not yet crossed out. This is a prime. If it is greater than the square root of n, go to step 5. Cross out all multiples of p which are not yet crossed out, go to 2. And then finally the numbers not crossed out are the primes not exceeding n. So interesting. Let's see, so you only need to start crossing out multiples at p squared because any small or multiple of p has a prime divisor less than p and has already been crossed out as a multiple of that. Wait, what? Okay, you only need to start crossing out multiples at p squared because any smaller multiple of p has a prime divisor less than p. So, like, if we're at the number 2, we only need to start crossing out multiples at 2 times 2, which is 4. Possibly a bad example. So, like, we get to 5. We can start at 25 because any smaller multiple of p has a prime divisor less than p. So, like, 10 has a prime divisor of 2, and 15 has a prime divisor of 3. Okay, I think that I kind of get it. I'm not sure I get it well enough to explain it to somebody who doesn't. But basically it's saying, okay, so, like, you get to this number that is prime. You say, okay, multiply that by 10. Or multiply that by itself. Any smaller multiple already has a different prime divisor. Okay, yeah. Makes sense. This is also the reason why we can stop after we've reached the square root of n. Because after that, it's not going to be... it's not going to be a prime number. Ooh. Oh, in our case, we actually can't stop after we reach the square root of n. Okay, I do not quite understand. Oh, okay. Okay, yeah. Okay, so, like, say we're trying to find primes below 10, but the square root of 10 is, like, between 3 and 4. And 5 and 7 are primes. Oh, the p can go up to square root of 10, I guess. Or square root of n. No, that still does not make sense. Okay, so let's look at the code and see if the code makes more sense to me. We begin with an implementation close to the description of the algorithm, which we will improve somewhat after having discussed it. For the list of numbers, we use a Boolean array, sieve, indicating which numbers have been crossed out. So cross limit equals... I'm not sure what these little symbols mean. I assume that it is making it an integer. So our sieve is going to be our new Boolean array of size, the difference between 2 and the limit, I think. Mark it as false. For n starting with 4 to limit with step 2. Mark even numbers greater than 2. Okay. Okay, so then we just set all the things to true. And then we do another for loop starting with 3 with step 2, so it'll go 3, 5, 7, etc. And if the sieve does not have... or if the sieve is not marked to true, it is prime. Okay. Marking to true means they are crossed off. So if not sieve, then we think it's then we know it's a prime number. And for m equal to, for 3 it would be 9 to limit with step 2 times n. So 6 sieve of m equals to true. So anything... Okay, so starting at the square of our n to limit with step 2 times n. Presumably to skip all the even numbers, I would say. Yeah, probably to skip all the even numbers. Cross off those. And then we calculate our sum by going through our sieve array and adding everything. That is adding all of the indexes that are not marked to true, that are marked to false. Okay. So, let's see if I figured it out after we read our explanation. So first we initialize the array to false because we have not yet crossed out any numbers. In crossing out, we discriminate between even and odd numbers, slightly deviating from the description. After all even numbers greater than 2 have been crossed out as multiples of 2, there is no point in crossing them out again as multiples of their odd divisors. So that's kind of what I was thinking. So when crossing out multiples of odd primes p, we can proceed in steps of 2p instead of p, sparing the even multiples. As noted above, all multiples of p less than p squared will already have been crossed out as multiples of smaller primes, so we need not revisit them. Also, if n is an odd composite, When the loop reaches n, that number and its multiples have already been crossed out, so we need not enter the inner loop then. Okay, so I think I kind of understand this, and I think that I'm going to try to implement it just to see if I can make it work. And then an easy optimization of the sieve is suggested by the discrimination of odd and even numbers. Apart from 2, all that the even numbers do is being crossed out once and occupying space. If we get rid of the even numbers, we save crossings out, and more importantly, we only use half the memory. That allows sieving larger ranges and reduces cache misses, thus improving performance. Sieving only odd numbers requires a bit of simple index arithmetics. We let the ith element of the array corresponding to the odd number 2i plus 1. So thus if p equals 2i plus 1, we find that p squared equals 4i squared plus 4i plus 1 has the index 2i, I plus 1. And if m equals k times p corresponds to j, then m plus 2p corresponds to j plus p. Okay, so if the ith index is not yet crossed out, the inner loop starts at 2i times I plus 1 and proceeds with step 2i plus 1. And this code becomes last index of the sieve. Sieve equals new Boolean array. Sieve bound false. Okay, I think I get now why they were saying you only have to look up to the square root of n. But I still don't quite understand. Okay, so because the numbers that are prime will have been not crossed out. Okay, yeah, that makes sense to me now. Because once you hit the square root of n, you're not going to get a multiple of any of the numbers between that number and n. Okay, so sieve bound is this limit minus 1 divided by 2, which is the last index. Sieve equals new Boolean array initialized to false. Cross limit is this limit minus 1 divided by 2 for I to 1 from 1 to cross limit. If not set to false, then this is prime, mark the multiples. Okay. And then again, we just kind of sum them up. Let's try the non-optimized version first. So let's see, we set our limit, which I did pull into a variable. We set our cross limit, which is the square root of that limit. And then we set up our sieve as a Boolean array. So let's do a little bit of Google search here. So Python initialize Boolean, and arrays are called lists in Python with all false. The list comprehension. Okay. So if I do something like this, it'll be sufficient. So going back, we have our limit, we need a cross limit. Let's go ahead and rename this, or yeah, let's go ahead and rewrite it. It'll be fine. Yeah, cross limit. Sorry. Cat is chewing on things again that the cat is not supposed to chew on. Different cat than the one that showed up in my last video. limit, and let's use the same method that we used elsewhere, where we just do this. And then see if IE or EI. According to this document we're working off of, IE. So sieve equals, and in this case we want false, for I in range and the last one should be limit, right? So false for I in range limit. Let me double check. Okay. Almost feel like a dictionary would work just as well, if not better, but let's not overcomplicate things. So in our case, the index, the I, is going to start at 0. And it's going to go up to all of these numbers. And I guess it doesn't really matter if the index goes all the way up to 2 million, because again, we know 2 million isn't prime. It's obviously divisible by 10 and possibly 100. Possibly, definitely 100 and 1,000. Okay, so in 4 to limit with step 2, we just set all of the even numbers. Ooh, can we set our list comprehension to do this part for us? Okay, could just do this. Okay. Let's not bother. Let's go ahead and just do it manually. And I am going to go ahead and just comment out all of this for right this minute. So let's go ahead and say n in range 4 to limit. N equals true. That's exactly what they have here in our little algorithm we're copying, yes. Okay, and then starting with 3. Yep, gotta do the range. Oh. What did we forget here? We forgot to add the step of 2, because otherwise it's just going to cross out everything. For n in range starting with 3, going to the limit, stepping by 2. If sieve of n is false, then it is prime. If not sieve n, then for all the numbers from n squared to the limit with a step of 2 times n, we mark to true. For m in range. I do really like the Python range method, apparently. In times n, comma, limit, in step of 2 times n, so 2. I think I have to use the time symbol. Oh goodness. Typing's still not my best skill right at the moment. And we really just want to say C of M, you're true. Yes? Yeah. And then of course the summation at the end for index value in enumerate. I'm using this function because I am learning it. I want to actually remember it next time I'm quizzed. Oh, we gotta make a little sum value variable or it won't work, will it? And I think I can do plus equals. Plus equals index actually is what I want. And I only want that if value, or rather if not value, sum plus equals index, and then we will print sum. And then I'm actually going to go all the way down here and uncomment this line in particular so that we still get our little date. Okay, so this is actually... Let's see, is this fewer lines of code or about the same? It's about the same, let's be real. Maybe 1 or 2 fewer lines, but it does a lot fewer calculations. We're only going through things like 1 time. Let's go ahead and see, when we run this, how long it takes and whether we get the correct number. We do not, because plus equals is not supported. Okay, fine. We won't use the little cute little shortcut here. Oh, well, maybe if I hadn't typoed my variable, we wouldn't be having this problem. Let's put that plus equals back, because I'm curious. Oopsies. So it was like, oh, you don't have a variable named sum, because I typed 2 U's. Okay, now we've got a number. But it is not, in fact, the same number, because we wanted to start at a different index. We wanted to skip indexes like 0 and 1, I think. So, let's see what we can do here. So, see 0 equals true. C of 1 equals true. There's almost certainly a better way of doing that, but that should at least get us to print out the correct number, which again is, let's go ahead and copy this again and put it up top so we can more easily compare it. Doop, doop, doop. Okay, so now we are getting 192, 913, 828, 922, which is the correct answer, and now we are getting it in 0.6 seconds. instead of 9 minutes. So yeah, obviously, because of course it is. It's way more efficient. So I'm going to go ahead and delete all of this. I think that our solution for finding whether a number is prime is one of the more efficient solutions, but it is not an efficient way of finding a large number of prime numbers. So yeah, let's see. So we have learned that when working with prime numbers, there's things ancient Greek people came up with that are way better algorithms than what we can come up on the fly in 2 minutes. Alright, so I'd say let's call it there for today. I might want to release an edited version of this tomorrow, but I think I'll just release the full version today. And I'll see you all in the next one.